Okay, welcome back to Ye Olde Physics Dungeon. Um, Today's the second lesson on sound, and we're going to look in detail at two things. One is interference and anything similar to interference that we can get sound to take part in, and the other is the Doppler effect. So first, I want to just mention that we have been using for about 15 years now a technology called active noise cancellation, most recently in some expensive headphones, which is basically just purposeful destructive interference. There's a microphone that picks up unwanted sound, and then the speaker in your ears puts out identical sound that is completely out of phase with the unwanted noise. Before you get too far into the lesson, you should pause and read through the webpage that's at the link in the supplement to the notebook if you're interested in how any of that works. Okay, now that you've read a little bit about interference, I'd like you to try, and it's a little bit weird doing this through the phone, through the video, but I'd like you to try to tell among these two tones. I'm going to play these two tones in a second. Just try and tell for yourself which one is the higher pitch, which one sounds like a higher frequency. Here's the first one. I'll call this number 1. And here's number 2. Again. Even if we were in person, I would claim that nobody in the room could actually tell the difference between those two. The human ear typically, on average, cannot tell the difference between two frequencies unless it's at least 3 hertz. I will tell you now that one of these two plays the note 440, which is an A, and the other one plays 441. What that means is that each second, the two tones together will be completely in phase and then completely out of phase once each second. That means that one beat will be heard, or we would say that the beat frequency is 1 when we play them together. So here that is. Again, I'm not so sure how well this comes across in the video, but what you hear once a second is that there is constructive interference, and also once a second there's destructive interference, because I will reveal to you this one is the 440 and this is the 441. So the first tone earlier was slightly lower than the second tone. Let's play you that beat frequency of 1 more time. You probably hear it as loud, quiet, loud. You should check out a couple of visualizations of this. One of them is on Desmos, and another one is, I guess, Pop Culture Famous. I'll see if I can track that down now. Okay, here are a couple of examples that I have laying around for beats. The first one comes from a machine that is at school. This shows in wet erase marker, or overhead projector marker, 20 wavelengths. This was created by a turntable, and the turntable rotated, but there was this axle that made it so that the marker didn't rotate around in circles, even though it was attached to it in some way. Instead, it just moved side to side. And then the paper was dragged out from underneath the tip of the marker, and so it made these 20 waveforms. At the same time, the machine was attached to a second turntable that made these 22 waveforms. And when the machine was turned on both turntables, oh, how the turntables turn, over the same width that they made 20 and 22 waves, respectively, they produced this pattern, which has a beat frequency of 2. It shows that in 2 places over that interval, they had constructive interference, and in 2 other places, they had completely destructive interference. This is a mechanical way to produce a pattern found here. I don't know if the kids are listening to the Arctic Monkeys anymore, but this is an album cover from them from a few years ago. Okay, we're moving on to the Doppler effect with sound, and unfortunately, with us doing this from home, there's no way not to miss out on what's a pretty cool day in class. I had the seniors fill out an exit survey where they described their most favorite demonstrations from the last couple years, and this was a very popular one. During the school day last fall, we went outside with a recording device, and we had Dr. Smith drive by at some speed that we didn't know, and we used the Doppler effect and our Doppler effect equations to figure out exactly how fast he was traveling on the road past the school. So here's a reminder. This is what the Doppler effect is about. The Doppler effect occurs when the source of waves moves relative to an observer, and the wavelengths and frequencies that are observed are different from the ones that are produced. In particular, if the source of the waves, being this car, is moving from left to right on the screen, indicated here by the speed of the source being to the right, the person in front of the car, or that is being approached by the car, will observe higher frequencies and shorter wavelengths than they typically would have. The person that the car is receding from observes low frequencies and long wavelengths. According to me, in your water waves lesson, the Doppler effect relationship can be summed up by the new wavelength that is observed is equal to the original one minus or plus the speed of the source times the time period of the original waves. I say according to me because this is not the way that the IB communicates this idea. Also, this only works when the source of the sound is the reason for the Doppler effect. The source moving is the reason for the Doppler effect. So if this car moves toward this person, we'd say that the speed of the source not being 0 is the cause for the Doppler effect. You can also experience the Doppler effect with a stationary car by running toward it or running away from it. In your Doppler effect tutorial that was assigned and is due the day that you're watching this video or the day that this video has been posted, you will have proven that when the source of the sound moves, this equation, which is an IB data booklet version of an equivalent expression to the wavelength relationship that I proved, this equation holds that the new frequency is the original frequency times this factor, and the data booklet actually doesn't have a minus or plus. They use a plus or minus, but you should know that the frequency is increased when the car approaches the person, or when this should be a minus, and that the frequency is decreased when it's a plus. If you did finish that tutorial homework assignment that is due the day that this video is posted, then here's the first proof that you did. It is that the Doppler effect also applies when an observer moves toward or away from a stationary source of sound. In this case, the expression, again, that's in your data booklet looks like this. And here's a quick explanation of what's experienced by everyone involved. Here, the source of the sound is stationary. An observer moving toward it will experience higher frequencies, shorter wavelengths, and a higher speed of the waves through the medium. At least they will observe the speed to be higher than it actually is passing through the medium. A person in the back, quote unquote, or a person who's moving away from the source of the sound will experience decreased frequencies increased wavelength, and effectively that type of relative motion is like slowing the speed of the waves through the medium. This is all handled, this situation is all handled in your data booklet with this equation. You notice here that the plus or minus is on the top of the equation, and that moving toward the source of the sound is as if the speed of the sound is increased. So here we do deserve or should have a plus on the top. The plus is for when the observer is approaching the sound, and the minus is for when the observer is moving away from the sound. So I tried to talk Dr. Smith into driving by your house with his horn on and then having you record the sound and calculate his speed from it. But he didn't take the offer. So we'll have to go with the numbers that we used last fall. So here are the numbers that we had in our experiment last fall with the current or graduating seniors. All that we knew when we started the experiment was the speed of sound, and then we recorded the sound of Dr. Smith going by, and it sounded higher pitched than what was actually being produced by the horn when he was approaching us. The frequency that we heard then when he was approaching in the front, I would say, was 980 hertz, and then when he receded from us, the frequency was dropped down to 882 hertz. And your goal is to find out how fast he drove past us. I suppose this says pause, there are spoilers ahead, but just kidding. It's your job to try to calculate his speed. This is the speed of the source of these sound waves. And what you know is that the frequency in the front is 980, in the rear is 882. So this is when approaching and receding. And you know that the speed of sound in air was 340 meters per second. You can do it. You should put your answer in meters per second into the Google form. That is, this will be the first question on the assignment for you to fill out on the form. The second response on your Google form assignment for today's lesson is related to another lab that we would have done had we met in class. So the idea here is this. There is a person walking toward other people. That person is holding up the source of sound that's playing a particular frequency. In this case, the frequency that is being played by that sound source and also the stationary one, the original frequency being put out is 800 hertz. What we were given, or would be given, or know, if we were doing this lab in person, is that the speed of sound is 1200 feet per second. And the question we would ask is, based on the number of beats heard by this observer, what speed is this person walking toward the group at? This person would measure the number of beats that they hear, or the number of loud, quiet, loud sounds that they would hear as this other person is approaching them, and we would write it down. We would time it. And so for this example, or for you to calculate, we will use that the observer hears, let's just put it here, they hear, we will say, 8 beats, or 8 loud, quiet louds in 3 seconds. And maybe before I just set you free and tell you to figure this out, the question being, what is the speed of the source of this sound? I should mention at least a few words about how you'll go about thinking about this. First of all, the reason that there are beats observed by this person is because of the Doppler effect. This sound source is putting out 800 hertz, and so is that one. But that person holding that 800 hertz sound source is moving toward these people. Just like Dr. Smith's car horn, when he was approaching us, sounded different. It sounded like it was at a higher pitch. This would as well. And so, because the observer experiences that at a slightly increased frequency compared to this 800 hertz, they hear beats. Based on the number of beats, the original frequency, and the speed of sound, it is possible for you to find the speed of the source. In other words, how fast this person is walking toward them. And that's your job for the second blank, the second question in your Google form. Good luck.